Reality has rules that break at the edges of the cosmos. We are about to cross 20 cosmic thresholds where space-time itself behaves in ways that defy all common sense. By the end of this journey, you will understand the profound forces that truly govern our universe. We will see how light can be trapped in a sphere of pure gravity, and why the vacuum of space is not empty at all. These are the frontiers where physics as we know it stops working. What single mystery of the universe most captivates your own sense of wonder? Crossing that threshold, you would find yourself in a place where the universe's own rules unravel. The event horizon is not a physical wall you could touch, but a one-way gate in the fabric of space itself. Imagine the gravity here is so overwhelming that the speed needed to escape is greater than the speed of light. Since nothing can travel faster than light, nothing, not even a single particle of light, can ever come back out. All possible paths for any object, for any information, lead only inward. The theories of brilliant minds like Stephen Hawking suggest that black holes are not the eternal prisons they seem. They may slowly leak a faint glow of radiation, a process that hints at a deep conflict between our understanding of gravity and quantum mechanics. This is the information paradox, a puzzle about whether anything that falls in is truly lost forever. From the outside, watching someone approach the event horizon would be a strange and gradual farewell. They would appear to slow down, their signals stretching into deeper and deeper red, until they simply freeze and fade from view. Their time, from your perspective, has effectively stopped. But from their perspective, crossing over might be uneventful, a silent passage into the unknown. This cosmic boundary forces us to confront the most fundamental questions. What happens to the laws of physics in a place of infinite density? Is information, the blueprint of reality, truly destroyed? The event horizon is the ultimate cosmic curtain, and pulling it back might reveal a new layer of existence we have yet to comprehend. But beyond that point of no return lies a region of even stranger activity. Around a spinning black hole, the distortion of spacetime creates a second boundary, an oval-shaped region of pure cosmic turbulence called the Ergosphere. Here, the black hole's immense rotation draggles the very fabric of space and time around with it, a phenomenon known as frame dragging. Imagine spacetime not as a static stage but as a swirling, cosmic whirlpool. Within the Ergosphere, it is utterly impossible to stand still. The universe itself is moving beneath your feet, forcing you to circle the black hole at incredible speeds. This is not a matter of powerful winds or forces you could resist. It is the stage itself rotating, and you are merely a player upon it. This bizarre property leads to one of the most incredible theoretical ideas in physics, the Penrose process. A daring civilization could, in principle, fly into the Ergosphere, jettison a piece of mass, and fly out again with more energy than they started with. They would have literally stolen rotational energy from the black hole itself. This challenges our most fundamental conservation laws and hints at a universe where energy is not always where or what we think it is. What could humanity achieve if we ever learned to tap into such a power source? The Ergosphere shows us a cosmos that is not merely curved, but actively dynamic, a spinning engine of unimaginable power. This violent twisting of reality inevitably leads us to wonder about places where the fabric of spacetime is not just warped, but severed completely. This violent twisting of reality inevitably leads us to wonder about places where the fabric of spacetime is not just warped, but severed completely. What if the universe itself is threaded with tunnels, cosmic shortcuts that bypass the vast emptiness between the stars. These are wormholes, theoretical passages also known as Einstein-Rosen bridges. They are not just science fiction, they are valid, though highly speculative, solutions to Einstein's equations of general relativity. Picture the universe as a vast, flat sheet of paper. A wormhole is like a fold that brings two distant points into direct contact, a tunnel burrowing through the higher dimensions we cannot see. The most treacherous part of this tunnel is its throat, a narrow, unstable region where the curvature of spacetime becomes extreme. Passing through this throat could, in theory, transport you across the galaxy in an instant, or perhaps even to a different time entirely. Yet this incredible possibility comes with a profound cosmic catch. Keeping such a tunnel from instantly collapsing requires something truly bizarre, exotic matter. This is not merely unknown matter, but a substance that possesses negative energy density, effectively pushing spacetime outward to prop the wormhole open. While quantum mechanics allows for tiny amounts of such negative energy, the quantities needed to stabilize a traversable wormhole remain far beyond our reach. The existence of a stable wormhole would rewrite the rules of the cosmos, creating a network of interstellar highways and raising the specter of time travel paradoxes. Could you travel back and prevent your own journey? The very laws of physics may conspire to prevent such logical knots, perhaps through mechanisms we do not yet understand. While we dream of stepping through a cosmic doorway, another threshold takes us to a moment where all of reality was born from a singularity. Before that first moment of existence, our understanding of reality dissolves into pure potential. We have reached the Planck Epoch, the very dawn of time, a fleeting interval so brief it defies human comprehension. From the universe's birth to approximately 10 to the negative 43 seconds later, conditions were so extreme that the very ideas of time and space lose all meaning. In this primordial state, gravity was not a gentle force but a quantum entity, as powerful as the other fundamental forces. The smooth, continuous spacetime we move through today did not exist. Instead, the cosmos was a seething, turbulent quantum foam. Picture a bubbling cauldron on the smallest possible scale, where tiny bubbles of space and time continuously form and vanish. Distances and durations fluctuated wildly, with geometry itself in a state of constant, violent change. This is the ultimate frontier of physics, a realm where our two most successful theories, general relativity and quantum mechanics, both fail. Unlocking the secrets of the Planck Epoch is the primary goal of a theory of quantum gravity, an attempt to describe how the cosmic stage itself was built. How did this chaotic, frothing sea of potential settle into the vast, orderly expanse we see today? The answer lies in a process called symmetry breaking, a cosmic cooling that may have cast the fundamental laws of nature into their current form. This mysterious origin, where everything began from almost nothing, set the stage for the universe's first great expansion. Sometimes the grandest structures in the cosmos begin with the smallest of flaws. In the first moments after the Big Bang, as the newborn universe expanded and cooled, it may have undergone a series of rapid phase transitions. Think of it like water freezing into ice. When ice forms quickly, the crystal structure is not perfect. It develops cracks and flaws locked into its new state. The universe may have done the very same thing, creating cosmic strings. These are not strings in any ordinary sense. They are hypothetical, one-dimensional defects in the fabric of spacetime itself. Imagine a thread of pure energy, thinner than a proton, yet so dense that a single inch of it could weigh more than a mountain. Such a string would be under immense tension, and its presence would warp the geometry of space around it. a cosmic string would act as a perfect gravitational lens. If one passed between us and a distant galaxy, we would see a double image of that galaxy, a ghostly duplicate created by the string's profound distortion of light. These relics from the universe's infancy could have served as cosmic seeds. Their immense gravitational pull might have guided the first clouds of gas and dust, influencing the formation of the very first galaxies and the large-scale structure we observe today. The hunt for their signatures is ongoing. Astronomers search for those telltale double images or for strange, sharp ripples in the cosmic microwave background. Finding one would be like discovering a fossil from the first moments of time, a linear scar on the cosmos that shows us how reality itself crystallized. These linear distortions show us how the universe's own birth defects shaped its future, but our view is also constrained by a fundamental cosmic boundary. Our view of the cosmos is fundamentally limited by a final, absolute boundary. We can only ever see the portion of the universe from which light has had time to travel to us since the very beginning, a frontier known as the Cosmological Horizon. This is not a physical wall at the edge of space, but a horizon in time, a limit set by the finite speed of light and the age of the universe itself. Every day, as more light from increasingly distant galaxies finally completes its billion-year journey to Earth, this horizon slowly expands, bringing new regions of spacetime into our observable realm. Yet for every new star that winks into view, an even vaster and unobservable cosmos remains forever hidden beyond that edge. We have no way of knowing what lies in those regions, whether they are filled with islands of galaxies similar to our own or something entirely alien and unexpected. This leads to one of cosmology's most enduring puzzles, the horizon problem. When we look at the cosmic microwave background, the faint afterglow of the Big Bang, we see that it is almost perfectly uniform in temperature. But regions on opposite sides of the sky were once so far apart that not even light could have traveled between them to equalize their conditions. How then did they reach the same temperature? The leading explanation is a period of cosmic inflation, a moment of unimaginably rapid expansion in the universe's first fraction of a second that stretched a tiny, uniform patch into our entire visible cosmos. The cosmological horizon is a humbling reminder of our place in the grand scheme. We are not at the center of the universe, we are at the center of what we can see, a single bubble of observation adrift in a possibly infinite whole. What strange geometries or different fundamental laws might govern the universe beyond our sight? This expanding frontier of observation forces us to confront regions where the very expansion of space becomes the dominant, overwhelming force. The expansion of the universe is not a journey through space, but a stretching of the stage itself. This fundamental motion is known as the Hubble Flow, a cosmic drift where galaxies are carried apart from one another as the fabric of spacetime expands. Picture the universe as the surface of an inflating balloon with galaxies like dots on that surface. The dots are not actively crawling across the balloon, they are simply being carried apart as the rubber stretches. This is why more distant galaxies appear to recede from us faster than nearby ones, a relationship described by the Hubble-Lemaitre law. The farther away a galaxy is, the more expanding spacetime there is between us, and thus the greater its apparent speed. At truly colossal distances, this cumulative stretching results in recession velocities that exceed the speed of light. This does not violate Einstein's cosmic speed limit, because those galaxies are not moving through space faster than light. The space between us is simply growing. The rule applies to motion through the cosmos, not to the expansion of the cosmos itself. This relentless stretching has profound consequences for the future of everything we see. It influences how galaxies evolve, how clusters form, and it dictates the ultimate fate of the cosmos. Will the expansion continue forever, slowing to a gentle coast, or could it one day reverse? The answer depends on a silent, ongoing battle between the outward push of dark energy and the inward pull of gravity, a competition that shapes the largest structures in existence. The cosmic tug-of-war between expansion and gravity has a final frontier for every massive structure. For any galaxy or cluster, there exists a precise boundary known as the turnaround radius. At this specific distance, the outward pull of the universe's expansion is perfectly balanced by the inward grasp of local gravity. Picture a vast, invisible sphere drawn around a giant cluster of galaxies. Within this bubble, gravity is the master. Galaxies can orbit each other, merge, and form larger structures held together against the cosmic tide. But venture beyond this invisible line, and you cross a point of no return. There, the relentless stretching of spacetime takes command, sweeping galaxies away in the Hubble Flow. They become cosmic driftwood, carried forever into the expanding darkness, never to interact with the cluster again. This radius is not static, it evolves over billions of years. In the early universe, when matter was denser and dark energy's influence was weaker, these gravitational spheres of influence were far larger. Today, dark energy's push is causing the turnaround radius to gradually shrink for many structures, isolating islands of galaxies from one another. This defines the ultimate fate of our own local cosmic neighborhood. Our Milky Way, Andromeda, and a few dozen smaller galaxies are all gravitationally bound, destined to eventually merge into a single, giant galaxy. But every other galaxy group and cluster lies beyond our turnaround radius. They are already receding from us, and one day, in the far future, they will vanish beyond our cosmological horizon forever. This fundamental threshold forces us to confront the scale where the local rules of physics we know are overruled by the universe's overall geometry. While this balance dictates the fate of the largest structures, the influence of dark energy is felt even in the emptiest regions of space. Just outside a black hole's event horizon, gravity orchestrates a cage made of pure light. This is the Photon Sphere, a theoretical boundary where photons, the particles of light, are forced into perfect circular orbits. For a simple, non-rotating black hole, this sphere sits at exactly 1.5 times the radius of the event horizon. Here, the pull of gravity is so perfectly tuned that light itself becomes a captive satellite, perpetually falling around the black hole without ever escaping or plunging inward. From a vantage point within this sphere, the cosmos would appear as a profoundly distorted theater. You would witness the entire universe wrapped around you in a brilliant, infinite annulus of light, a complete circle of distorted galaxies and stars. Any light you emit could still escape, but its path would be bent into a tight spiral, creating multiple, ghostly images of every celestial object for any distant observer. This intense gravitational lensing would turn the black hole into the ultimate funhouse mirror for the universe. What would it be like to stand within a sphere of orbiting light, watching the fabric of reality twist around you? This bizarre behavior of light is a direct consequence of spacetime being curved to its absolute limit, a curvature so severe it warps not just the paths through space, but the very flow of time itself. Deep within the twisting core of a rotating black hole, a second, more profound boundary awaits. This is the Cauchy Horizon, the final threshold where the known laws of physics are not just bent but utterly shattered. It is a frontier of pure unpredictability. According to general relativity, as you cross this inner horizon, all the light and radiation that has ever fallen into the black hole converges upon you. This cosmic traffic jam of energy becomes infinitely blue-shifted, compressed into a wall of unimaginable intensity. Theoretically, this could create a singularity not of matter, but of pure energy, a firewall that would instantly end any journey. Yet the true mystery of the Cauchy Horizon is not just this violent energy, but what it means for reality itself. This is the point where determinism fails. The entire premise of physics, that knowing the present allows us to predict the future, collapses here. Beyond this horizon, the future is no longer determined by the past. The path ahead could branch into an infinite number of possibilities, perhaps even into other universes or regions of space-time with entirely different physical laws. How would reality function in a place where cause and effect are no longer linked? Some theories suggest that the infinite energies might actually act to destroy the inner horizon, preventing its existence and preserving the laws of physics as we know them. This cosmic censorship hypothesis proposes that nature abhors such naked unpredictability, veiling it from the wider universe. The Cauchy Horizon forces us to confront the deepest nature of reality, questioning whether the orderly cosmos we observe is the only possible version, or merely one thread in a vast, tangled tapestry of existence. This chaotic frontier where prediction dies stands in stark contrast to the serene and uniform emptiness that characterizes the vast expanses between galaxies. Black holes are not the simple, featureless voids they once seemed. They possess a hidden complexity, a form of cosmic disorder known as entropy. This profound idea, pioneered by Jacob Bekenstein and refined by Stephen Hawking, forever linked the world of thermodynamics to the realm of extreme gravity. Entropy is a measure of the number of ways a system's internal components can be rearranged without changing its overall appearance. A messy room has high entropy, as there are countless ways the clothes and books could be scattered while still looking messy. A black hole from the outside appears to be defined by only three things: its mass, its spin, and its charge. It is the ultimate tidy room, seemingly devoid of any internal detail. Yet Bekenstein and Hawking showed that a black hole's entropy is not just large, it is colossal, and it is directly proportional to the surface area of its event horizon. The larger the black hole, the more surface area its horizon has, and the greater its entropy. This was a staggering revelation. It meant that black holes are not cold, dead endpoints. They are thermal systems with a temperature, and they can radiate energy, a slow leak now known as Hawking radiation. But this connection between surface area and disorder led to an even more radical idea. If a black hole's entropy, its hidden information, is proportional to its surface area, then perhaps all the information about everything that has ever fallen into it is not lost inside, but is instead encoded on its two-dimensional boundary, the event horizon. This is the heart of the holographic principle, a concept that suggests our three-dimensional reality, with all its richness and depth, might be a projection from a two-dimensional surface, much like a hologram emerges from a flat piece of film. How does the entropy of a black hole relate to the information it contains? It implies that the universe itself might be storing its data on its outermost shell, and the world we experience is a magnificent, detailed illusion. This threshold is a crucial bridge, forcing gravity and quantum mechanics to speak the same language and suggesting that space-time is not fundamental, but emerges from something deeper. These thermodynamic whispers from the edge of a black hole push us to explore how quantum effects can reshape the very vacuum of space. Even the most perfect cosmic prison cannot hold everything forever. Stephen Hawking revealed that black holes are not truly black, but instead glow with a faint heat, slowly evaporating back into the universe. This Hawking radiation arises from the bizarre quantum nature of the vacuum of space. At the very edge of the event horizon, pairs of virtual particles continuously flicker in and out of existence. Normally, these particle and antiparticle pairs annihilate each other almost instantly. But when this happens right at the precipice, one particle can be captured by the black hole's immense gravity while the other escapes into space. To conserve energy, the particle that falls in must have negative energy, which effectively reduces the black hole's mass. This slow, steady leak means that over immense timescales, a black hole will gradually shrink, its event horizon receding until it vanishes entirely in a final, theoretical flash of energy. This process shatters the classical view of black holes as eternal fixtures. They are born, they live, and they die, possessing a finite temperature and a lifespan measured in trillions upon trillions of years for stellar mass black holes. Yet this elegant solution creates one of the most profound puzzles in modern physics, the black hole information paradox. According to quantum mechanics, information about the state of a physical system can never be truly destroyed. But if a black hole evaporates completely, what happens to all the information about every star, planet, and atom that ever fell into it? Is that information lost forever, radiating away in a formless heat glow, or is it somehow preserved and returned to the universe in the final evaporation? This paradox pits the fundamental rules of quantum theory against the predictions of general relativity, and its resolution may require us to rewrite our understanding of reality itself. As we ponder the ultimate fate of information, we are drawn to the next threshold, where the very fabric of spacetime is born from a sea of quantum uncertainty. The silent engine driving our universe's accelerating expansion is dark energy, a force woven into the very fabric of empty space. Unlike gravity, which pulls matter together, dark energy exerts a kind of negative pressure, causing spacetime itself to stretch at an ever-increasing rate. Its simplest mathematical description is the cosmological constant, a term Einstein once introduced and later discarded. He called it his greatest blunder, but modern observations of distant supernova have revealed that this cosmic repulsion is not only real, it dominates the universe's energy budget. This energy density is incredibly faint, yet because it is a property of the vacuum, it is constant and uniform everywhere. As the universe expands and matter dilutes, gravity's pull weakens, but dark energy's push remains steady, eventually becoming the dominant force on cosmic scales. The origin of this energy is one of physics' most profound puzzles. Quantum field theory suggests that the vacuum should be seething with a much larger energy density, creating a discrepancy between prediction and observation, so vast it is often called the worst theoretical prediction in the history of science. Why is the cosmological constant so exquisitely fine-tuned to the tiny, non-zero value we observe? The answer might lie in a new dynamic field, or perhaps in the landscape of possible universes predicted by string theory. This constant, gentle pressure is shaping the ultimate destiny of everything, leading us toward a future of cosmic isolation and cold, empty expansion. What does it mean for our universe that its dominant component is a force we cannot see and barely understand? This pervasive, mysterious energy is the backdrop against which all other cosmic dramas play out, its subtle influence felt even in the most extreme environments. Yet the ultimate fate of information falling into a black hole leads us to a far more fundamental boundary, a realm where the very concept of space and time dissolves. We have reached the Planck density. This is the maximum possible density of matter and energy in our universe, a staggering 5 × 10⁻96 kilograms per cubic meter. To grasp this number, picture compressing the entire observable universe into a volume smaller than a single atom. At this extreme, the smooth, continuous stage of spacetime described by Einstein's general relativity shatters. The gentle curves of gravity are replaced by a violent, chaotic froth, a turbulent sea of quantum fluctuations where tiny bubbles of space and time continuously pop in and out of existence. This is the domain of quantum gravity. How does spacetime behave when probed at this ultimate scale? It becomes grainy and discrete, more like a cloud of pixels than a smooth sheet. Distances and durations lose their fixed meaning, fluctuating wildly in a state of pure potential. This regime is not just a theoretical curiosity, it is the state of the entire universe in the first fleeting moment after the Big Bang, and it is the condition we believe exists at the very center of a black hole at the singularity. Our current laws of physics simply fail here, unable to describe a reality where the stage itself is boiling. Unlocking this threshold requires a theory that unites the vast scales of gravity with the tiny quantum world, a final theory of everything. What would it mean to see the universe not as a continuous expanse, but as a tapestry woven from individual, fundamental threads? The extreme densities of this quantum era connect directly to the strange nature of the vacuum itself, a seeming emptiness that is anything but empty. The vacuum of space is not a silent void but a vibrant, seething sea of potential. This restless energy reveals itself in a subtle but measurable force, the Casimir Effect. Picture two perfectly smooth, uncharged metal plates placed incredibly close together in an otherwise empty vacuum. According to classical physics, nothing should happen between them. But the quantum world tells a different story. The narrow gap between the plates restricts the kinds of virtual particles that can flicker into existence, while outside the plates, a much wider spectrum of these fleeting particles can appear. This difference in quantum activity outside versus inside creates a subtle pressure, pushing the plates together with a faint, undeniable force. It is as if the silent hum of the universe itself is nudging them to close the gap. This is not just a theoretical curiosity, it has been experimentally confirmed. The Casimir Effect is direct proof that what we call empty space is a cauldron of activity, with virtual particle pairs dancing in and out of reality on timescales so short they evade direct detection. This ceaseless activity means the vacuum has a real, fluctuating energy density. By placing those plates, we are not just observing this energy, we are manipulating it, creating a region of lower energy density between them compared to the outside. In doing so, we are subtly altering the local geometry of spacetime itself, demonstrating that quantum mechanics can warp the cosmic stage on the tiniest of scales. This raises a profound and tantalizing question. If we can already influence the energy of the vacuum, could we one day learn to harness these quantum fluctuations for practical purposes? Imagine a spacecraft not propelled by burning fuel, but by surfing the very fabric of spacetime, using the endless churn of the quantum sea for thrust. While such technologies remain far in the future, the Casimir Effect stands as a testament to a universe where nothing is truly at rest, and where the emptiness between stars holds the key to untold possibilities. This active nature of the vacuum forces us to consider the next frontier, where spacetime is not just observed but actively engineered. The quantum sea is not merely a passive background, it is a material we could one day learn to shape. A spacecraft could ride a wave through the cosmos, not by pushing against anything, but by commanding the fabric of spacetime itself to move around it. This is the principle behind the Alcubierre warp drive, a speculative but mathematically valid concept in general relativity. The ship rests inside a stable bubble, a pocket of normal spacetime. Ahead of the bubble, the fabric of the universe is compressed, pulling the destination closer. Behind it, space-time is dramatically expanded, pushing the point of origin away. The vessel itself never moves through the local space inside its bubble, thus never violating the cosmic speed limit. It is the bubble that travels, carrying the ship along like a surfer on a wave of distorted geometry. This incredible feat requires something truly exotic, negative energy densities, to warp the space-time continuum into this specific configuration. This is the same bizarre substance theorized to hold a wormhole open, a form of matter with a gravitational repulsion. While quantum field theory allows for tiny amounts of such negative energy, the colossal quantities needed for a macroscopic warp drive are far beyond any technology we can envision. The very act of creating such a warp bubble would have profound consequences. Some calculations suggest that particles could accumulate at the front of the bubble, building up to dangerous energy levels and blasting the destination with a shower of radiation upon arrival. Others raise the possibility that the warp bubble could be catastrophically unstable, or that it would require manipulating fundamental constants in ways we cannot yet predict. This represents our ultimate threshold of cosmic engineering, where we would no longer be travelers in space-time, but its architects. What would it mean for humanity to grasp the controls of the cosmic stage itself, to fold the universe to our will? This dream of engineering reality pushes us to consider the next frontier, where the universe's own rulebook might not be as constant as we believe. One of the most trusted pillars of physics is the constancy of the speed of light, a universal speed limit etched into the fabric of reality. But what if this constant has not always been constant? Some cosmological theories dare to suggest exactly that, proposing that in the searing heat of the early universe, light traveled faster. This idea of a varying speed of light offers a radical solution to puzzles like the horizon problem. If light moved immensely faster in the first moments, it could have crisscrossed the cosmos, smoothing out temperatures long before the universe expanded enough to isolate those regions. This would render the period of cosmic inflation unnecessary, replacing one profound mystery with another. The implications ripple through every law of physics. The speed of light is not just a number, it is woven into the very equations that define reality, from Einstein's iconic E equals mc squared to the fundamental structure of spacetime itself. If C were different, the delicate balance of forces that allows atoms and molecules to exist would shift. The causal connections that let one event influence another would be rewritten, potentially altering the story of how galaxies and stars first formed. This challenges our deepest assumptions about the stability of nature. Are the constants of physics truly fixed, or are they merely local bylaws, evolving over cosmic time or changing in different corners of the multiverse? How would our understanding of the universe transform if its most fundamental rules were not written in stone, but in shifting sand? The possibility of inconstant constants leads us to thresholds involving the very dimensionality of spacetime, where the stage of reality may have more hidden dimensions than we ever perceived. Our familiar three dimensions of space might be an island in a far vaster cosmos. This is the startling proposal of brain cosmology, where our entire universe is a three-dimensional membrane, or brain, adrift within a higher dimensional reality known as the bulk. In this view, the particles and forces that make up our world are stuck to our brain like ink on a page. They cannot leave the surface they inhabit. Gravity, however, is different. It may be the one fundamental force that can leak across dimensions, spreading out into the bulk. This could explain its profound weakness compared to the other forces. The electromagnetic force is stronger by a factor of 10 to the 36, a number so large it defies comprehension. If gravity's influence is diluted by spreading into these extra dimensions, its apparent feebleness in our world suddenly makes sense. Some of these extra dimensions could be compactified, curled up into loops so tiny that we could never perceive them directly. Others might be large but remain inaccessible because all matter and energy except gravity are confined to our own brain. How could we possibly detect such a hidden architecture? One tantalizing clue would be the discovery of miniature black holes. Particle colliders like the Large Hadron Collider might, for a fleeting instant, create these tiny gravitational pits if extra dimensions exist, providing a portal to the bulk. Another signature could be found in the precise orbits of planets. If gravity is seeping into other dimensions, its force might weaken at very small distances in a way that Newton's law does not predict. This model even offers a breathtaking new origin story for everything. The Big Bang itself might not have been a singularity in time, but a colossal collision between our brain and a neighboring one, a cosmic shockwave that filled our membrane with the energy to create galaxies, stars, and ultimately, us. Are we living on a vast dynamic sheet, one of many floating in a higher dimensional sea? The search for these hidden dimensions is a quest to understand the true, and likely very strange, topology of spacetime. The very geometry of reality might permit journeys into yesterday. Kurt Gödel, a colleague of Einstein, discovered a startling solution to the equations of general relativity that describes a universe in uniform rotation. In this Gödel universe, the fabric of spacetime is twisted by this overall spin into pathways called closed time-like curves. An astronaut following such a path would find themselves traveling through space only to return to their exact starting point, not just in location but in time. They could, in theory, arrive back at the moment they left or even before. This is not science fiction, but a mathematically valid, if deeply strange, possibility within our best theory of gravity. Such a loop immediately raises the specter of paradox. Could you travel back and prevent your own birth? This classic grandfather paradox challenges the logical consistency of the universe, suggesting that cause and effect could become untangled. The Gödel universe itself is homogeneous, meaning it looks the same at every point, but it is not isotropic. It has a preferred direction, an axis of rotation that gives the cosmos a cosmic swirl, breaking the symmetry we observe in our own universe. While astronomical evidence strongly indicates we do not live in such a spinning cosmos, its existence as a valid solution is profoundly important. It demonstrates that the engine of general relativity can produce spacetimes where the river of time flows in a circle. How would the laws of physics maintain their integrity in a reality where the future could influence the past? Some physicists suggest that quantum effects or a principle of self-consistency would simply prevent any logically contradictory actions from occurring. You would be free to travel to the past, but never able to change it in a way that creates a paradox. The existence of these closed time-like curves forces us to ask if time is a fundamental river flowing in one direction, or merely an emergent property, a local rule that can be rewritten by the right cosmic geometry. This ultimate threshold of time loops brings us to the final frontier, where the very act of looking at the universe may determine what it becomes. The final cosmic threshold is not found in the depths of space, but in the very act of looking itself. Quantum mechanics presents us with a world that remains a blur of possibilities until the moment it is measured. In the famous double-slit experiment, a single electron behaves as a wave, passing through both slits at once and creating an interference pattern, a ghostly fingerprint of its simultaneous journeys. Yet the instant we set up a detector to see which slit it goes through, the electron snaps into a single, definite location, and the interference pattern vanishes. This is the quantum measurement problem, the profound mystery of how the mere act of observation, seems to collapse a spread-out wave of probability into a concrete point of reality. How does this process of observation relate to the stage of spacetime? Some interpretations, like the many worlds theory, propose a radical answer. They suggest the wave function never collapses at all. Instead, at each moment of measurement, the entire universe splits, branching into a multitude of parallel realities. In one world, you see the electron go through the left slit. In another, an identical version of you sees it go through the right. Every possible outcome is realized somewhere, in a vast, ever-dividing multiverse where spacetime itself continually forks into new histories. This challenges our most basic assumption that spacetime is the fundamental arena of the cosmos. Perhaps it is not. Perhaps spacetime, along with the definite events that happen within it, emerges from a deeper, more abstract quantum reality, a reality that only appears solid and singular from our limited, branching perspective. Does the universe require a conscious observer to define its properties, or does consciousness itself emerge from a cosmos where all possibilities are equally real? This is not merely a philosophical debate, it is a question that strikes at the heart of what is real. We have journeyed across 20 cosmic thresholds, from the event horizon of a black hole to the quantum foam at the beginning of time. We have seen how spacetime can be warped, twisted, torn, and perhaps even created by observation. Each threshold reveals a universe far stranger, more dynamic, and more interconnected than we ever imagined. They show us that the rules we take for granted are not universal laws but local customs, valid only within our particular bubble of reality. The greatest discovery is not any single answer, but the vastness of the questions that remain. The cosmos is a story still being written, and we are both its readers and its authors. Each threshold we have crossed reveals a piece of a much larger puzzle. The photon sphere's cage of light is not separate from the quantum foam of the Planck Epoch, and the dark energy driving cosmic expansion is intimately linked to the Casimir Effect's restless vacuum. These are not isolated oddities, but interconnected symptoms of a deeper reality we are only beginning to grasp. Black hole thermodynamics points toward a holographic universe, where information is stored on a two-dimensional surface. This same principle may govern the cosmological horizon, the ultimate boundary of our observable cosmos. The forces that isolate galaxies at the turnaround radius are the very same ones that dictate the stability of a wormhole's throat. Every scale, from the smallest quantum fluctuation to the largest cosmic structure, is woven together by a single, coherent fabric. Our current theories are like separate maps, brilliantly detailed for their own territories but failing where the landscapes merge. General relativity charts the continents of gravity and spacetime, while quantum mechanics maps the bustling cities of particles and forces. Yet at their borders, the maps contradict each other, leaving vast, unexplored regions. This is why the quest for a theory of quantum gravity is so vital. It is the search for a unified map of reality, one that can guide us from the boiling frenzy of a singularity to the serene expansion of the cosmos. How might such a complete understanding transform our place in the universe? It could reveal new principles of energy, allowing us to harness the vacuum itself or navigate the folds in spacetime. Beyond technology, it challenges our most fundamental philosophies. If the universe is a holographic projection, what does that say about the nature of our own consciousness and reality? Contemplating these connected thresholds does not provide final answers, but it refines the questions, preparing us to see the grand tapestry of existence not as a collection of parts, but as a single, unfolding story. We have journeyed across the strange and beautiful frontiers of our cosmos, from the silent prison of the event horizon to the seething quantum foam of the vacuum. These 20 cosmic thresholds are more than just scientific curiosities. They are profound reminders that the universe operates on a logic far grander and more intricate than our everyday experience suggests. They challenge the very foundations of how we perceive time, space, and cause and effect, revealing a reality that is dynamic, interconnected, and deeply mysterious. Each new discovery at these frontiers does not simply provide an answer. It refines our questions, pulling back another layer of the cosmic veil to show us how much more there is to learn. The greatest lesson from this journey is one of humility and wonder. Our understanding of physics is not a completed book, but a living story, constantly being rewritten by the cosmos itself. I would love to hear which of these thresholds captured your imagination most profoundly. Was it the photon sphere's cage of light, the paradoxical nature of time loops, or the holographic encoding of reality? Share your thoughts in the comments below. If these mysteries of space and time inspire you, please subscribe for more journeys to the edge of understanding. And always remember to look up at the night sky, for it is a window into a universe that is endlessly surprising, waiting for the next curious mind to discover its secrets.